For over 5 decades, the lunar surface has remained a silent witness to humanity's retreat to low Earth orbit. Since the final dust settled behind the ascent stage of Apollo 17 in December 1972, the Moon has transitioned from a physical destination back into a celestial mystery, hanging in the night sky as a reminder of a capability we once possessed, and then, through a complex interplay of politics and shifting priorities, chose to relinquish. Today, we are witnessing what astronomers and historians alike are calling the Artemis Awakening. This is not merely the development of a new rocket or a singular mission to plant a flag. It is a fundamental restructuring of our relationship with the deep void. The Artemis program, named for the twin sister of Apollo, represents a massive technological and ideological shift that seeks to transform the Moon from a place of brief visitation into a permanent, sustainable base of operations for the human species. At the heart of this awakening is the Space Launch System, or SLS, the most powerful rocket ever successfully flown. Standing nearly 100 meters tall, the SLS utilizes a combination of heritage hardware and modern manufacturing. Its core stage is powered by 4 RS-25 engines, the same liquid hydrogen and liquid oxygen engines that once propelled the space shuttle, now optimized for the extreme thermal and structural demands of deep space injection. Flanking this core are 2 massive 5-segment solid rocket boosters, providing the initial 8.8 million pounds of thrust required to break the heavy chains of Earth's gravity. But the hardware is only part of the story. The awakening is also reflected in the Orion multi-purpose crew vehicle, a spacecraft designed to sustain 4 astronauts for up to 21 days in the harsh radiation environment of cislunar space. Unlike the Apollo command modules, which were confined by the limited computing power of the 1960s, Orion features a glass cockpit architecture and advanced autonomous systems that allow for high-precision navigation and environmental control. However, as the program moves toward its first crewed flight, Artemis Roman II, the reality of modern spaceflight is setting in. The recent postponement of missions, often triggered by technical flaws uncovered during rigorous testing, such as the wet dress rehearsal, serves as a sobering reminder that the vacuum of space remains an unforgiving laboratory. These delays are not merely bureaucratic hurdles. They are the result of a commitment to safety protocols that were written in the blood of previous generations. In the current era, the tolerance for risk is significantly lower than it was during the Cold War sprint of the 1960s. This slower, more methodical pace is a defining characteristic of the Artemis story. It reflects a shift from the high-stakes gamble of flags and footprints to a strategy of incremental validation. Scientists are now focused on the south pole of the Moon, specifically the South Pole-Aitken Basin, where permanently shadowed craters harbor volatile resources that were invisible to the Apollo missions. The scientific rationale for this return is grounded in the discovery of water ice sequestered in these permanently shadowed regions, or PSRs. These craters have not seen sunlight for billions of years, creating thermal traps where temperatures plummet below 30 Kelvin. Within these dark pockets, spectroscopic data from lunar orbiters has confirmed the presence of hydrogen-rich deposits. For a lasting human presence, these deposits are more valuable than gold. Water ice can be electrolyzed into liquid oxygen for breathing and liquid hydrogen for rocket propellant, effectively turning the Moon into a cosmic refueling station. This concept of in situ resource utilization, or ISRU, is the cornerstone of the Artemis Awakening. It is the bridge between a one-off mission and a sustainable civilization beyond Earth. Yet, as we stand on the precipice of this new chapter, we must confront the fatigue point mentioned by contemporary observers. The excitement of a launch is often tempered by the reality of long-term funding and political will. The Artemis program operates within a global framework known as the Artemis Accords, a multinational agreement that seeks to establish norms for lunar exploration and resource extraction. Unlike the unilateral race of the 1960s, this is a coalition effort involving the European Space Agency, JAXA, and the Canadian Space Agency. This collaboration provides a measure of stability against the shifting winds of domestic politics, but it also introduces complex layers of diplomatic and technical synchronization. The awakening we see today is a response to 5 decades of planetary stagnation. We are no longer content with looking at the moon through telescopes. We are preparing to integrate it into our economic and scientific sphere. But as we move forward, the historical comparison with Apollo looms large. We are promised a future of lunar cities and Martian expeditions, yet the technical realities suggest that the road will be long, expensive, and fraught with setbacks. The Artemis Awakening is the first step in a slow and steady climb toward the stars, a process of relearning how to live and work in an environment that is fundamentally hostile to our biology. It is a moment of profound transition, where the echoes of the past meet the ambitions of the future, and the true measure of success will not be the first bootprint of the 21st century, but the decision to stay. The countdown clock is perhaps the most iconic symbol of the space age, a ticking representation of human ambition distilled into seconds and milliseconds. But in the modern era of the Artemis program, that clock has become a source of profound psychological and technical tension. To understand the current state of lunar exploration, one must look past the polished animations and the heroic rhetoric to the gritty, unglamorous reality of the vehicle assembly building. On February 3rd, the momentum of the Artemis II mission encountered a familiar and sobering adversary: the technical postponement. This delay, triggered by flaws uncovered during the high-stakes wet dress rehearsal, serves as a case study in why the future we were promised often feels so agonizingly out of reach. These are not merely bureaucratic hiccups. They are the result of a fundamental collision between cutting-edge physics and the extreme conservatism of modern aerospace engineering. To appreciate the difficulty of the mission, one must first understand the complexity of the wet dress rehearsal itself. This is the final and most critical hurdle before a rocket is cleared for flight. During this procedure, the nearly 100-meter-tall Space Launch System is loaded with more than 700,000 gallons of cryogenic propellants, supercooled liquid hydrogen, and liquid oxygen. This is a delicate thermal ballet. Liquid hydrogen must be maintained at a temperature of -423 degrees Fahrenheit. At these temperatures, the very molecules of the metal structure begin to contract and shift. Seals that are airtight at room temperature suddenly become porous. Hydrogen is the smallest atom in the universe, and its ability to find the most microscopic leak in a pressurized plumbing system is a legendary nightmare for engineers. If a single valve fails to seat properly, or if a sensor provides an anomalous reading, the entire operation must be scrubbed. In the context of the February 3rd delay, these technical flaws were not signs of failure, but rather the system working as intended, identifying risks before they can manifest as a catastrophic loss of crew. Yet, for a public raised on the high-speed narratives of the 1960s. These repeated delays contribute to a growing sense of mission fatigue. We are living in a paradox where our technology is exponentially more advanced than that of the Apollo era, yet our path to the moon feels slower and more tentative. This technical reality is rooted in the architecture of the SLS itself. It is a heritage rocket, meaning it utilizes components derived from the Space Shuttle program, such as the RS-25 engines and the solid rocket boosters. However, integrating legacy hardware with modern digital flight computers and the high-performance Orion capsule creates a Frankenstein of engineering challenges. Every time a component is upgraded, the entire systemic model must be revalidated. Unlike the Apollo program, which operated with a higher tolerance for risk and a singular, focused goal of beating a geopolitical rival, the Artemis program must navigate a landscape of extreme accountability and multi-decadal sustainability. The cost of a single SLS launch is estimated in the billions of dollars, a figure so staggering that a single failure could theoretically end the entire program. This financial pressure forces a slow and steady approach that is scientifically sound but politically and socially exhausting. Furthermore, we must consider the physiological and environmental constraints of the Orion spacecraft. Designed to sustain a crew of 4 for up to 21 days, Orion represents the absolute limit of our current life support capabilities in deep space. It must scrub carbon dioxide, maintain a precise atmospheric mix, and shield its occupants from the unattenuated radiation of the Van Allen belts and solar particle events. Every postponement lengthens the time these sensitive systems sit on the pad, exposed to the humid, salty air of the Florida coast, which introduces its own set of corrosion and degradation risks. The fatigue point mentioned by observers is a reflection of this broken timeline. When we look at the historical comparison with Apollo, we see a program that went from a standing start to a lunar landing in 8 years. Artemis has already been in development for over a decade, and we have yet to see a human being leave low Earth orbit. This delay creates a vacuum in the public imagination, often filled by skepticism, and a sense that the Apollo future was a temporary anomaly rather than a permanent trajectory. The technical flaws of the wet test are reminders that space is not just hard. It is a domain where the laws of thermodynamics and material science do not care about our political cycles or our desires for a speedy return. In the hangar, away from the cameras, the work continues with a methodical, almost agonizing precision. Engineers must diagnose why a specific sensor tripped or why a cryo-coupling leaked. They must simulate the failure, test the fix, and then wait for the next narrow window of opportunity. This is the unglamorous heart of modern spaceflight. It is a world of broken timelines and revised schedules, where success is measured not by the speed of the journey, but by the integrity of the hardware. As we move toward the eventual launch of Artemis II, we must reconcile ourselves to this slow, steady reality. The moon is only 240,000 miles away, but the distance between a successful test and a sustained human presence is measured in the thousands of small, corrected flaws that the public rarely sees. The fatigue we feel is the price of a future that is being built to last, rather than just to arrive. The shadow of the Apollo program looms over the modern space age like a colossus, a golden era of fire and ambition that fundamentally redefined what the human species deemed possible. To understand why the Artemis program feels like a departure from this storied past, We must first dissect the unique biological and mechanical intensity of the 1960s. Apollo was not merely an exploration program. It was a geopolitical weapon, a high-velocity technological sprint fueled by a seemingly bottomless well of national treasure and a tolerance for risk that would be unthinkable in the modern regulatory environment. In less than a decade, humanity moved from the first tentative suborbital leap of Alan Shepard to the majestic lunar descent of Neil Armstrong and Buzz Aldrin. This rate of progress was an anomaly in the history of science, a statistical outlier that created a permanent distortion in our collective expectations of the future. The centerpiece of this era was the Saturn V rocket, a machine of such raw, overwhelming power that its ignition could be detected by seismographs hundreds of miles away. The Saturn V was a three-stage masterpiece of liquid-fueled engineering. Its first stage, the S-1C, utilized 5 F-1 engines, each generating 1.5 million pounds of thrust by burning a mixture of refined kerosene, known as RP-1, and liquid oxygen. This was the pinnacle of the combustion age of rocketry. The second and third stages utilized liquid hydrogen, an incredibly volatile but efficient fuel that allowed for the high-velocity translunar injection burn. But for all its magnificence, the Saturn V was a disposable titan. It was designed for a singular purpose: to deliver a small capsule to the moon and return its occupants safely. It was not an infrastructure. It was not a highway. It was a spear thrown into the dark. When we compare this to the modern space launch system and the Artemis program, the contrast in philosophy is striking. Modern observers, including aerospace historians, often point to a looming sense of mission fatigue. This fatigue is rooted in the realization that while Apollo was a sprint, Artemis is attempted as a marathon with a fraction of the relative budget. The lessons from the golden age of rocketry suggest that flags and footprints do not constitute a lasting presence. The Apollo missions were magnificent, but they were fundamentally short-sighted in their lack of a sustainable logistics chain. Once the geopolitical objective was achieved, and the funding began to evaporate in the early 1970s, the entire architecture of lunar exploration was dismantled. We were left with a legacy of artifacts in museums rather than a thriving economy in orbit. The Apollo future we were promised, one of lunar cities and regular interplanetary travel, was a mirage because it lacked the foundational sustainability that the modern era is desperately trying to build. Scientifically, the leap from Apollo to Artemis is measured in more than just decades. It is measured in the transition from analog to digital reality. The Apollo guidance computer featured roughly 4 kilobytes of random access memory, less power than a modern electronic greeting card. Navigation was a manual, painstaking process involving sextants and star sightings. In contrast, the Orion spacecraft utilizes advanced autonomous systems and high-fidelity sensor suites that can process terabytes of data in real time. This technological sophistication allows for far more complex mission profile, targeting the lunar South Pole. This is a region of extreme topography and permanent shadows that would have been a death trap for the Apollo landing craft, which required flat, sunlit plains for their primitive landing radars to function. Yet, the fatigue point mentioned by contemporary critics is real. In the 1960s, the public was fed a narrative of constant, linear advancement. Every month brought a new record, a new milestone. Today, the delays of the wet dress rehearsal and the technical flaws uncovered in modern testing feel like a betrayal of that narrative. but history suggests that the slow and steady approach, while frustrating to the observer, is the only way to ensure that this time, when we go, we stay. The echoes of Apollo remind us that raw power is enough to arrive, but only a methodical, sustainable infrastructure is enough to inhabit. The historical comparison also forces us to look at the human cost and the organizational culture of NASA. During Apollo, the average age of the engineers in mission control was just 26. They were learning the physics of orbital rendezvous and docking in real time, often inventing the mathematical proofs hours before they were needed. Today, the industry is more mature, more bureaucratic, and arguably more cautious. This caution is justified by the immense cost of modern hardware, but it creates a psychological barrier. We are no longer willing to lose a crew to the vacuum, and thus we find ourselves in an endless cycle of testing and postponement. Ultimately, the lesson of Apollo is one of both triumph and tragedy. We proved we could reach the moon, but we failed to prove we could live there. Artemis represents the hard work of correcting that failure. It is the transition from being a species that visits the moon to a species that integrates the moon into its economic and scientific sphere. The echoes of Apollo serve as a reminder of what is possible when will and resources align, but they also serve as a warning. If we do not build for the long term, if we do not prioritize slow and steady progress over the spectacular but fleeting individual mission, we risk repeating the retreat of 1972. The future Artemis is starting is not the one promised in the 1960s brochures, but it is the one that might actually endure. For as long as humanity has looked toward the stars with the intent of exploration, the red planet has served as the ultimate siren song, a rust-colored destination that appears deceptively close in the telescopic lens, yet remains agonizingly out of reach. This is the Mars Mirage, a psychological and technical phenomenon that has defined the last 50 years of aerospace history. Since the 1960s, every generation has been told that a human landing on Mars is exactly 20 years away. It is a shifting horizon that recedes at the same rate we attempt to approach it. To understand why this promise remains unfulfilled, we must look at the profound divergence between the lunar missions we are currently reviving and the staggering physical realities of a true interplanetary voyage. The genesis of this mirage can be traced back to the height of the Apollo era. In 1969, as the world celebrated the triumph of the Sea of Tranquility, Wernher von Braun presented a formal plan to the Nixon administration. It was a bold, comprehensive architecture that envisioned a human landing on Mars as early as 1981. In that optimistic vacuum, the moon was merely a practice range, a high-altitude proving ground for the nuclear thermal rockets and rotating artificial gravity spacecraft that would inevitably follow. But the historical comparison with Apollo reveals a harsh truth about the interplay of space, politics, and money. Apollo was a sprint fueled by a unique geopolitical engine that consumed nearly 5% of the United States federal budget. Once that engine was dismantled, the Mars promise collapsed into a series of white papers and conceptual animations. The scientific gap between the Moon and Mars is not merely a matter of distance. It is a fundamental shift in the scale of risk. A mission to the Moon is a 3-day journey across 250,000 miles. If a technical flaw occurs, as it did during the Apollo 13 mission, the free return trajectory and the proximity of Earth offer a narrow but viable path home. Mars, however, is governed by the rigid clockwork of celestial mechanics. A mission to the red planet typically utilizes a Hohmann transfer orbit, an elliptical path that requires a 6 to 9 month transit through the deep space radiation environment. Once a crew commits to that trans-Martian injection burn, they are effectively exiled from the human race for up to 3 years. There is no aborting a mission to Mars halfway through. During this transit, the biological toll on the human frame becomes a primary scientific hurdle. Beyond the protective magnetosphere of the Earth, astronauts are exposed to a relentless bombardment of galactic cosmic rays and potential solar particle events. These high-energy heavy ions can slice through cellular DNA, increasing cancer risks and potentially compromising neurological function. Furthermore, the prolonged exposure to microgravity results in significant bone density loss and muscular atrophy. Even with the advanced exercise equipment currently tested on the International Space Station, a crew arriving at Mars after 9 months in zero-G would likely be too physically weakened to execute a complex landing and surface operation. The technical realities of the Martian atmosphere introduce further complexity. While the Moon is a perfect vacuum, allowing for the use of simple descent engines and landing radars, Mars possesses a thin, carbon dioxide atmosphere that is roughly 1% the density of Earth's. It is a scientific no man's land. The atmosphere is too thin to provide enough drag for massive parachutes to slow down a heavy human-class lander, yet it is thick enough to generate extreme frictional heat during entry, requiring heavy thermal protection systems. Solving the problem of entry, descent, and landing for a vehicle weighing 20 metric tons is a challenge that current technology has yet to master. This brings us to the critique of the Artemis program as a precursor to Mars. Critics often argue that individual missions, while visually spectacular, do not equate to a lasting presence. Artemis Roman II, a mission designed as a lunar flyby, is often compared to Apollo 8. While it validates the Orion spacecraft's deep space life support and the Space Launch System's performance, it does little to address the fundamental logistics of a Mars mission. To break the cycle of the Mars Mirage, we would need more than a few landing missions. We would need an entire infrastructure of orbital fuel depots, nuclear-powered transit vehicles, and sustainable life support systems that do not rely on constant resupply from Earth. History suggests that the slow and steady approach is the only way to avoid the fatigue point where public interest and political funding evaporate. Every administration since the 1970s has announced its own Mars plan, only to have the succeeding administration cancel it due to cost or shifting priorities. This policy whiplash is the matryoshka doll of aerospace editing, layer upon layer of revised goals that prevent any single architecture from maturing. The Mars Mirage persists because we have historically prioritized the cool, individual mission over the unglamorous, expensive work of building a permanent highway through the void. As Artemis Roman II prepares for its journey, the shadow of Mars still hangs in the background, a reminder that the future we were promised in 1969 requires more than just a return to the Moon. It requires a fundamental commitment to the slow, agonizing work of conquering the physics of the deep solar system. Until then, Mars remains a beautiful, distant possibility, always 20 years in the future. The transition from the fleeting exploration of the mid-20th century to the sustained habitation of the 21st century represents perhaps the most significant evolutionary hurdle for the human species. While the Apollo era proved that we could touch the lunar surface, it did not prove that we could survive there. True sustainability beyond the protective cocoon of low Earth orbit is not merely a matter of hardware. It is a complex, multidimensional challenge involving thermodynamics, orbital mechanics, and the fundamental limits of human biology. To build a lasting presence, we must move away from the model of the self-contained capsule and toward an integrated, regenerative ecosystem that views the moon not as a destination, but as a source of life and propellant. At the center of this sustainable horizon is the concept of in situ resource utilization, or ISRU. In the Apollo era, every liter of water and every breath of oxygen had to be hauled up from the bottom of Earth's massive gravity well at an astronomical cost. For Artemis to succeed where its predecessor retreated, it must harvest the resources of the lunar environment itself. The primary focus of this scientific endeavor is the lunar South Pole, specifically the Shackleton crater and the surrounding South Pole-Aitken basin. Here, the axial tilt of the moon creates regions of permanent shadow where temperatures have remained below 30 Kelvin for billions of years. These cold traps are thought to contain significant deposits of water ice and other volatiles. The scientific process of transforming this ancient ice into usable resources is a marvel of chemical engineering. Through electrolysis, water molecules can be split into hydrogen and oxygen. The oxygen provides a breathable atmosphere for lunar habitats, while the hydrogen, when liquefied and recombined with oxygen, serves as high-performance rocket propellant. This essentially transforms the moon into a deep space gas station, providing the energy required for landers to ascend back to orbit or for future spacecraft to push onward toward the Martian frontier. Without this capacity to live off the land, any lunar base remains a fragile outpost, tethered to a vulnerable and expensive supply chain from Earth. However, the challenges of a lasting presence are not limited to fuel and air. Biological sustainability remains an unforgiving frontier. When astronauts leave the protection of Earth's magnetosphere, they are exposed to a relentless bombardment of ionizing radiation. This includes both the constant drizzle of galactic cosmic rays and the sudden, violent bursts of solar particle events. Unlike the short 3-day sprints of Apollo, long-duration Artemis missions will expose crews to cumulative doses of radiation that significantly increase the risk of cancer and neurological degradation. Building a sustainable habitat requires more than just pressurized walls. It requires the use of lunar regolith as a shielding material. Scientific models suggest that burying habitats under several meters of processed lunar soil can attenuate these high-energy particles, creating a radiation environment comparable to that on Earth. Furthermore, we must address the structural sustainability of the infrastructure itself. The lunar environment is characterized by razor-sharp regolith, microscopic shards of glass formed by eons of micrometeoroid impacts. Without the weathering effects of wind or water, these particles remain jagged and highly abrasive. During the Apollo missions, this dust clogged seals and degraded spacesuit fabrics in a matter of days. A permanent presence requires advanced materials science to develop dust-tolerant mechanisms and self-healing seals. It also necessitates the development of lunar manufacturing, using techniques like solar sintering or microwave heating to turn raw regolith into roads, landing pads, and bricks, preventing the dangerous sandblasting effect caused by rocket plumes. The orbital architecture of Artemis also introduces a new kind of sustainability, the Lunar Gateway. Positioned in a near-rectilinear halo orbit, or NRO, the Gateway serves as a permanent harbor between Earth and the Moon. This specific orbit is a masterpiece of gravitational balancing, allowing the station to remain visible to Earth-based antennas at all times, while minimizing the fuel required for station keeping. It acts as a staging point for both human and robotic missions, allowing for the reuse of landing vehicles and the long-term storage of supplies. By establishing this high-ground infrastructure, NASA and its international partners are attempting to create a stable, predictable highway to the surface, reducing the risk and cost of each individual descent. Yet, as observers of the program often point out, technical feasibility is not the same as political or economic sustainability. The slow and steady approach favored by historians is a response to the fatigue point that has killed so many previous Mars and Moon initiatives. True sustainability requires a commitment that outlasts political administrations and budget cycles. It requires the integration of private industry, such as the massive reusable architectures of the SpaceX Starship, to drive down the cost per kilogram of mass delivered to the surface. It also requires the international cooperation enshrined in the Artemis Accords, ensuring that the exploration of the Moon is a collective human endeavor rather than a unilateral sprint. The horizon we are looking toward is one where the Moon is no longer a strange world we visit, but a familiar extension of our own planet. It is a world where we have mastered the cycles of oxygen and water, where we have learned to shield our bodies from the fire of the sun, and where we have built machines that can endure the abrasive touch of the lunar night. This isn't the flashy, high-speed future promised in the brochures of the 1960s, but it is a future built on the hard-won lessons of history. It is a future where we go to the Moon not to prove a point, but to build a home. The true measure of success for Artemis will be the moment when the lunar surface is no longer a place of silence, but a place of work, science, and the quiet, rhythmic hum of a life sustained. The lunar surface remains the most expensive piece of real estate in the solar system, not because of its intrinsic value, but because of the staggering amount of kinetic energy required to reach it. In the vacuum of space, every gram of mass is a financial liability, and for the Artemis program, the greatest obstacle to progress is not the physics of the vacuum, but the complex, shifting landscape of terrestrial economics and political cycles. To understand the cost of the Moon, we must examine the interplay between the massive infrastructure requirements of deep space exploration and the fragile nature of long-term government funding. While the Apollo program was a sprint fueled by an existential geopolitical conflict, Artemis is a marathon conducted in an era of fiscal scrutiny and mission fatigue. This transition from a wartime footing to a sustainable exploration model has created a series of technical and financial paradoxes that define the modern space age. At the center of this economic debate is the Space Launch System, or SLS. Each launch of this titanic vehicle is estimated to cost approximately $2 billion, a figure that includes not just the fuel and hardware, but the massive standing army of engineers and technicians required to maintain the vehicle assembly building and the mobile launcher. Unlike the commercial sector, which has embraced the cost-saving potential of reusability, the SLS remains a fully expendable architecture. It utilizes the RS-25 engines, exquisite pieces of engineering that once served as the reusable heart of the space shuttle, and discards them into the Atlantic Ocean after a single use. From a strictly scientific perspective, this is a loss of highly refined heritage hardware. From a political perspective, it is a method of maintaining a specialized industrial base across multiple states. This tension between industrial stability and launch efficiency is one of the primary reasons why the Artemis timeline often feels broken. The transcript of modern aerospace history is filled with what critics call the matryoshka dolls of policy editing. This refers to the layers of revised goals and shifting destinations that have plagued NASA since the end of the Apollo era. One administration prioritizes a return to the lunar surface. The next redirects the focus toward a captured asteroid. A third demands a direct path to Mars. Each shift in the narrative requires a fundamental re-engineering of the hardware, leading to the massive cost overruns and delays that contribute to public fatigue. This lack of a singular, unchanging objective prevents the slow and steady progress that history suggests is the only viable path in space. When a mission like Artemis II is postponed due to technical flaws uncovered during a wet dress rehearsal, it isn't just a schedule slip. It is a drain on the limited pool of political capital that sustains the program. Furthermore, we must consider the scientific cost of short-sightedness. As contemporary observers note, having a handful of individual landing missions does not constitute a lasting presence. To stay on the moon requires the construction of infrastructure that does not yet exist. Lunar power grids, autonomous mining equipment for water ice, and pressurized habitats that can withstand the 14-day lunar night. Building this infrastructure requires a level of funding that far exceeds the budget for individual cool missions. The scientific community is currently grappling with the reality that the cost of reaching the moon may consume the very resources needed to do science once we arrive. This is the interplay of space, politics, and money in its most literal sense. We are building a high-speed highway to a destination where we have yet to build a house. The fatigue point is also a biological and psychological reality. During the 1960s, the public was captivated by the rapid succession of Mercury, Gemini, and Apollo. In the modern era, the gap between Artemis I and the crewed Artemis II mission has stretched into years. During this interval, the technical flaws of the hardware, leaking hydrogen seals, software anomalies, and thermal protection concerns, become the primary narrative. The excitement of exploration is replaced by the unglamorous reality of troubleshooting. This slowdown is scientifically necessary to ensure the safety of the crew in an environment that offers no second chances, but it tests the patience of a society accustomed to the rapid iteration of the digital world. Ultimately, the cost of the moon is the price of our own indecision. If we prioritize the individual, spectacular mission over the boring work of sustainable logistics, we risk repeating the retreat of 1972. The Artemis program represents an attempt to build a future that is not just a repetition of the past, but a permanent expansion of the human sphere. To succeed, it must survive the matryoshka dolls of political change and the economic gravity of the space launch system. The lesson of the last 50 years is that the moon is not a place you visit. It is a place you inhabit through a slow, steady, and relentlessly funded commitment. The future we were promised in the golden age of rocketry is still possible, but it requires us to reconcile the high cost of the moon with the infinite value of staying there. As Artemis II sits on the pad, it is more than just a rocket. It is a $4 billion question mark regarding humanity's ability to commit to a horizon that lies beyond the next election cycle. To move beyond the familiar confines of our own gravitational cradle is to confront a scale of distance and danger that effectively renders our current technological prowess primitive. While the Artemis program represents a significant reawakening of human ambition, the transition from lunar exploration to true interstellar capability requires a fundamental reimagining of what it means to architect the void. We are no longer talking about individual missions or fleeting visits. We are talking about the construction of a permanent, self-sustaining infrastructure that can endure the staggering physics of the vacuum for centuries. As contemporary observers of the Artemis Roman II mission note, the fatigue of delays and the technical flaws of chemical rocketry are symptoms of a civilization that is still learning to build for the long term. To reach the stars, or even to break the 50-year cycle of unfulfilled Martian promises, we must move away from the spectacular but isolated mission and toward a cohesive, interlocking architecture of deep space logistics. At the core of this future architecture is the concept of the orbital shipyard. In the Apollo era, and even with the modern space launch system, our vessels are designed to be launched directly from the Earth's surface, battling the immense friction of the atmosphere and the crushing pull of a 1G gravity well. This is an incredibly inefficient method of interstellar transit. A true interstellar infrastructure requires the assembly of massive, nuclear-powered transit vehicles in the permanent microgravity of high Earth orbit or at the Lunar Gateway. The Gateway, positioned in its near-rectilinear halo orbit, serves as the first high-ground harbor. By utilizing the Moon as a staging point, we can leverage the lower lunar escape velocity to launch heavier, more complex payloads that would be impossible to lift from Earth. This is the unglamorous but essential work of building a highway through the void, a process that requires the slow and steady commitment that aerospace historians argue is the only viable path to success. The scientific challenge of interstellar missions is primarily one of energy density and propulsion. The chemical engines we currently utilize, such as the RS-25 mentioned in the Artemis story, are limited by the energy stored in molecular bonds. To cross the light years between stars, or even to reduce the 6-month transit to Mars to a manageable duration, we must master the physics of nuclear thermal or nuclear electric propulsion. A nuclear thermal rocket utilizes a fission reactor to heat a propellant, such as liquid hydrogen, to extreme temperatures, achieving a specific impulse double that of the most advanced chemical rockets. This would allow us to break the cycle of unfulfilled promises by providing the power required for high-velocity trajectories that do not rely on the rigid launch windows of the Hohmann transfer. This is the what happens next that critics of the Artemis program are looking for, a transition from the heritage of the past to the physics of the future. However, the architecture of the void is not merely a matter of engines. It is a matter of shielding. Interstellar space is not a vacuum of nothingness, but a sea of high-energy ionizing radiation and galactic cosmic rays. To sustain a crew for decades or even lifetimes, we must move beyond the thin aluminum hulls of current spacecraft. Future interstellar missions will likely require matryoshka doll shielding, layers of diverse materials, including liquid hydrogen fuel tanks and thick sections of lunar-derived regolith, to attenuate these high-energy heavy ions. The technical flaws and safety postponements we see in current missions are the necessary proving grounds for these life-sustaining systems. We are learning, through the slow and agonizing process of troubleshooting on the Florida coast, the level of systemic reliability required to survive in an environment that offers no second chances and no hope of rescue. Furthermore, we must architect the communications and data infrastructure of the deep solar system. As a vessel moves further into the void, the traditional radio frequency links used since the 1960s become bandwidth-limited and prone to interference. A lasting presence beyond low Earth orbit requires the deployment of a high-speed laser communication network, utilizing the deep space optical communications technology currently being tested on missions like Psyche. This interstellar internet is the prerequisite for the remote operation of mining robots and the psychological health of crews isolated by the tyranny of light-speed delays. It is the invisible nervous system of our future expansion, a technological layer that must be built piece by piece, mission by mission. The historical comparison with Apollo reveals that our greatest failure was the lack of this foundational infrastructure. We had the fire, but we did not have the foundation. Artemis represents the attempt to correct this by building the gateway and the lunar habitats. It is the first layer of a matryoshka doll of missions that will eventually contain the architecture for interstellar transit. History suggests that the rush for cool, individual milestones leads to retreat, while the slow and steady accumulation of infrastructure leads to habitation. As we look toward the horizon, we must recognize that the moon is not the destination. It is the shipyard. The fatigue we feel today is the price of admission for a future where humanity is no longer a visitor to the void, but its primary architect. The future Artemis is starting is a world of permanent harbors and nuclear sails, a world where the stars are no longer points of light, but achievable coordinates in a slow, steady, and relentlessly built human highway. As we stand at the final coordinate of this examination, we must confront the most difficult transition in the history of human exploration. The shift from the exhilarating sprint of the 20th century to the methodical marathon of the 21st. For decades, the metric of success in space was defined by the binary logic of the Cold War. Did we arrive? And did we arrive first? This Apollo distortion has flavored our expectations for 50 years, creating a collective impatience that views every technical delay and every postponed wet dress rehearsal as a sign of institutional failure. But the reality of the Artemis program suggests that we are witnessing a fundamental redefinition of what it means to succeed in the deep void. Success is no longer measured by the height of a flag or the depth of a boot print. It is measured by the integrity of a seal, the reliability of a life support scrubber, and the decision to value the safety of a crew over the convenience of a political timeline. The technical postponement of the Artemis II mission on February 3rd, following flaws uncovered during the propellant loading process, is not a setback in the scientific sense. In the unforgiving physics of cryogenic rocketry, a delay is often the ultimate demonstration of success. It represents the triumph of a rigorous safety culture over the go fever that claimed the crews of the Challenger and Columbia. Modern aerospace engineering is navigating a level of complexity that is exponentially greater than that of the 1960s. The Space Launch System is a hybrid of heritage hardware and next-generation digital architecture, managing the thermal gradients of liquid hydrogen at -423 degrees Fahrenheit, while synchronizing millions of lines of flight code, requires a level of precision that cannot be rushed. The fatigue point often mentioned by critics is a byproduct of our desire for the cool, individual mission. But history suggests that the flashy sprint is precisely why we haven't been back to the moon since 1972. Redefining success in the new space race means embracing the slow and steady path. It means prioritizing the unglamorous construction of a lasting presence over the visually spectacular visitation. To stay on the moon, we must master the cycle of in situ resource utilization. We must learn to electrolyze lunar ice into oxygen and hydrogen, effectively turning the Shackleton crater into a metabolic and energetic hub. This is the what happens next that defines the Artemis awakening. If we simply land and leave, we have achieved nothing more than a high-fidelity repetition of the past. But if we build the infrastructure of habitats, power grids, and orbital harbors like the Gateway, we are architecting a future that is sustainable in the long term. This transition requires a psychological adjustment from the public. We must learn to find wonder not just in the fire of the launch, but in the quiet, rhythmic hum of a life support system that has functioned perfectly for months on end in the radiation-drenched environment of cislunar space. The interplay of space, politics, and money has historically created what we call the matryoshka dolls of mission editing, layer upon layer of revised goals that prevent any single vision from reaching maturity. Success in the modern era requires us to break this cycle. It requires a commitment to a singular trajectory that outlasts the 4-year cycles of terrestrial administrations. The historical comparison with Apollo reveals that our greatest weakness was our inability to sustain the momentum once the initial race was won. Artemis is designed to be the antidote to that retreat. It is a multinational coalition, grounded in the Artemis Accords, which creates a diplomatic and economic gravitational well that is much harder to dismantle than a unilateral government program. By distributing the technical and financial burden across international partners and private entities like SpaceX, we are building a diversified ecosystem that can survive the shifting winds of domestic policy. Scientifically, we are moving from the era of the pioneer to the era of the inhabitant. This requires a profound understanding of the biological toll of deep space. We are no longer content with surviving a 3-day journey. We are studying how to thrive for lifetimes. This involves the development of regolith-based shielding to protect against galactic cosmic rays, and the engineering of closed-loop ecological systems that can recycle 98% of all water and air. These are the technical realities that make the modern timeline feel broken compared to the 1960s, but they are the only realities that lead to Mars. A mission to the Red Planet is not a 3-day dash. It is a 3-year commitment to the clockwork of celestial mechanics. We cannot attempt that leap until we have proven our endurance on the moon. In the end, the future Artemis is starting is not the one promised in the mid-century brochures, but it is the one that is physically possible. The slow and steady approach is a recognition that the vacuum of space is a laboratory that does not tolerate shortcuts. Success is the slow accumulation of validated hardware, the methodical mapping of resources, and the steady expansion of the human sphere. As the SLS sits on the pad in Florida, undergoing the agonizingly slow process of troubleshooting and retesting, it is a testament to our maturity as a spacefaring species. We are no longer throwing spears into the dark. We are building a highway. The fatigue we feel is merely the friction of a civilization finally attempting to move its home beyond the atmosphere. If we stay the course, if we value the boring logistics of sustainability over the high-speed thrill of the sprint, then the moon will not be the end of the story, but the foundational harbor for our journey to the stars. Redefining success means realizing that the race is already over and the era of habitation has finally begun.